Thanks.
Huishan, could you give everyone a co-host so they can open their videos?
Okay, how do I do that?
No, sorry. Huishan, our assistant.
Okay.
Yeah, sure. By the way, we are going live in 5 seconds. 5, 4, 3, 2, 1.
Okay, good morning, good afternoon, good evening. Welcome back to session 4 of Material Intelligence conference. So session 4, we're chairing by Professor Xu Weishun, who is currently teaching at Zhejiang University, holds a master's degree from Harvard GSD, and who is focusing on the parametric design. He is working on numerous architecture projects in economics, political, and civil realms, as well as in the fields such as how to pronounce Tekanaka cooperation. So let's welcome Mr. Xu Weishun, chairing session 4. Welcome.
Thank you, Professor Yuan. Hello, everyone. Welcome back from the very short break. I'm Weishun Xu from Zhejiang University, and my teaching and research right now is mainly focusing on the computational design and fabrication, incorporating natural materials, including bamboo and clay. And I'll be chairing the session on materialization and construction. This is the last paper presentation session of this day and of this year's CDRF, and we have 7 presentations lined up for the following 2 hours, a little bit shorter than 2 hours, from researchers all over the world. So I would like to thank all of the presenters in advance for sharing your time with us today, and also congratulate you for the wonderful works that you have done. So without further ado, let's welcome our first presenter. Our first presentation is from the Institute of Computational Design and Construction in Stuttgart. And the work is co-completed by Ada Özdemir, Laura Kiesewetter, Laura Andreas Antorveza Páez, Tiffany Cheng, Samuel Leder, Dylan Marx Wood, and Achim Menges. I hope I'm getting all the names right. The topics on the hybrid additive manufacturing of oh, sorry, there's a, there seems to be an echo. The topics on the hybrid additive manufacturing of self-shaping material for construction of doubly curved shell structures. Okay, so without further ado, the stage is all yours if you're ready.
Thank you so much. I will share my screen and start right away. So I hope you can you all see the screen?
Yes.
Yes, perfect. Okay, so thanks for this introduction. Our paper is called Towards Self-Shaping Metamaterial Shells, a computational design workflow for hybrid additive manufacturing of architectural scale double curved structures. Shell structures are advantageous in architecture because apart from their simple and elegant aesthetics, the geometric stiffness resulting from their double curvature makes them highly material efficient. And while recent advancements in modeling and simulation technology gives us architects and engineers sophisticated tools to design these structures, creating double curvature with conventional construction techniques is still rather complex. The forming process often requires complicated subtractive machining or large formwork with excessive waste production. On the construction side, highly skilled manual labor is necessary to handle large formwork or intricate scaffolding. Therefore, this research proposes an alternative to contemporary shell construction practice. By using a material's intrinsic properties, forming instructions can be embedded into the material system so that the structure can be fabricated with additive manufacturing while in its flat state, and conventional forming methods can be replaced with self-shaping. For this, we use a hybrid material system combining self-shaping wood actuators with its tunable 3D printed metamaterial patterning. This way, the manufacturing is simplified because the structure is fabricated in the flat state and then autonomously self-shapes on-site into the pre-programmed double curved geometry. This research is positioned in the context of 3 major design fields: self-shaping structures, large-scale additive manufacturing, and bending active metamaterial surfaces. The principle of self-shaping wood is based on the intrinsic hygroscopic swelling properties of wood cells which take in or emit water depending on their surroundings' relative humidity. However, with cross-laminated wood bilayers, only single curvature can be achieved so far. Large-scale additive manufacturing is a high-resolution fabrication method. Lightweight, filigree structures can be printed with locally tunable properties and bent into shape. This allows for the creation of shell structures with little to no waste production, but still requires coordinated physical shaping on site. Auxetics are a subcategory of mechanical metamaterials that exhibit unusual behavior when bent or stretched. Their potential for architectural applications, however, has so far mainly been explored on a small scale. We are especially building upon these 4 selected research projects by using large-scale self-shaping wood for its structural capacity, large-scale additive manufacturing for mesoscale customization, and auxetic metamaterials for their ability to create double curvature. Our contribution is developing a computational design workflow for the hybrid material system of wood actuators and 3D printing materials introduced at the DigitalFUTURES 2018 workshop. To make self-shaping possible from flat components, we use wood bilayers as actuators that are embedded in the tunable metamaterial patterning, which on the other hand can be pre-programmed to exhibit anticlastic, single-curved, and synclastic surfaces when bent. This concept is investigated through the development of a computational design workflow that starts with the design of a double curved shell geometry, which is analyzed concerning its curvature and structural demands to inform the system parameters. Physical tests and a digital simulation tool are used to understand the mechanisms and to evaluate the resulting geometry's closeness to the design intent. With this information, the wood bilayers can be produced and the fabrication code generated. The machine instructions for the hybrid additive manufacturing come together with a custom fabrication sequence. First, the pattern is printed, the actuators are inserted, and finally enclosed with printed layers. After the fabrication, the structure is exposed to ambient conditions. The wood moisture content decreases, the bilayers start bending, and the structure self-shapes. Finally, the resulting shell structure is scanned for evaluation and comparison with the digital model. Karen, you're mute. Sorry.
Okay. Sorry. As mentioned, we conducted a series of physical and digital tests to explore the parameter with which we can control the self-shaping process. Physical tests on centimeter scale were produced, so they will curve in ambient interior conditions. But while these physical tests are very valuable for understanding the complex relationships between the various design parameters, they are also time-consuming. For this reason, they were complemented with a digital simulation tool, which uses a large deformation analysis in Caramba 3D. In this physical test, it can be seen how the metamaterial pattern can differentiate double curved surfaces, even though they are only actuated by a single curve actuator. These angle changes in the pattern structure are clearly visible in the simulation, where we see a color map indicating the areas of high positive and negative Gaussian curvature and the smooth transitions between them. Before testing the workflow on a large-scale prototype, we went through the steps with a scaled version. A surface with differentiated double curve is designed and then analyzed and flattened. Based on the Gaussian curvature, the pattern is generated. The actuator orientation is produced according to the main curvature directions. Finally, the height of the pattern is adjusted to reinforce it locally. Once all system parameters are set, the self-shaping behavior is simulated to compare the results with the design intent and to adjust parameters where necessary. The suggested configuration is then tested with a physical prototype that self-shapes under ambient conditions. The results have shown that the developed simulation tool produces reliable results at this scale. However, the main challenge of scaling up this system is the increased self-weight, By scaling up the system 10 times, the resulting structure weighs 1,000 times the initial pattern. Therefore, the choosing bilayer thickness ratio and pattern generation must be carefully reevaluated based on the described workflow. For the scaled-up prototype, the bilayers had to be designed and fabricated. The wood types for the active and restrictive layer are selected, and based on the expected curvature, a thickness ratio of both layers can be calculated. The other factors that influence the resulting radius are the grain direction and the relative humidity at which the active layer is equalized, which in our case we set to 92%. With this information, the wood actuators can be fabricated and stored in a humid environment until the start of the additive manufacturing process. For the demonstrator fabrication, we work with a large-scale additive manufacturing fabrication setup using a wood-based cellulose filled plastic composite as the printing material.
We designed the geometry with synclastic and anticlastic areas while taking into account the bilayer's radii limitations, material and pattern flexibility, and the fabrication constraints. Following the workflow we presented earlier, we generated the metamaterial pattern. Then different actuator configurations were simulated, and the one with the highest curvature and the smoothest curvature transition was chosen for fabrication. To reinforce the design, the local utilization values from the structural analysis of the chosen geometry were used to inform the depth gradient. Then, the simulation was used as a means to negotiate between the system parameters to find the ideal configuration that is closest to the design intent. In order to produce this design, we developed a custom one-line toolpath for our transitioning metamaterial pattern. The toolpath strategy consisted of 4 different layer types in which the actuators were placed manually. We manufactured our demonstrator in 15 hours. The printing was stopped as little as possible to ensure proper bonding between the layers and to avoid the bending of the actuators before the end of the production process. The self-shaping took 152 hours in indoor conditions. After around 72 hours, we realized that the actuation force of the bilayers was not enough to lift the self-weight and overcome the pattern stiffness. Therefore, we hung the prototype from a bar to reduce the impact of self-weight and friction for the rest of the shaping process. After the completion of self-shaping, we compared the simulation and the large-scale demonstrator to evaluate our workflow. The shape retention of the physical demonstrator was also verified by 3D scanning it and comparing the point cloud to the simulation. In a nutshell, we developed a computational design workflow for self-shaping hybrids, including a simulation for the prediction, and validated it with centimeter and meter scale prototypes. We implemented an optimized printing sequence for the metamaterial pattern and tested it within a robotic fabrication process. And finally, we showcased the potential of scaling up self-shaping wood and 3D printed metamaterial hybrids to achieve double curved shell geometries. While the pre-programming of the geometry and upscaling of this material system were successful, the self-shaping process could not be precisely predicted. The most notable issues were stress-related material failures in the pattern and the actuators. This could have been avoided if the prototype was supported from the beginning of the actuation by better integrating the actuators, modifying the pattern and printing material to change stiffness, and by improving the simulation accuracy through incorporating the moisture dependency of wood. Since the form needs to be stabilized after actuation, the addition of supports at the edges of the structure or the usage of tension cables could increase stability. And alternatively, our initial studies of pattern-integrated snap-fit locking mechanisms can be investigated further. We envision the construction approach that achieves complex 3D geometries from simplified 2.5D fabrication with the potential of reducing carbon footprints through flat pack transportation and decreasing labor and scaffolding by self-shaping on site. The research presented offers a low-impact solution for the construction of complex architectural structures, contributing environmentally and technologically to the way we build, taking a step towards more sustainable construction methods. We would like to thank our co-authors for their contributions to the paper and DigitalFUTURES for this opportunity to present our research. Thank you so much for listening. We're looking forward to your questions.
Thank you very much, Laura, Karen, and Ida. You presented very complex and I think comprehensive research on the challenging topic dealing with not only self-shaping geometries, but also multi-material hybrid digital fabrication. That needs to take so many factors into consideration. So everybody in the Zoom meeting, you can either use the chat box or use the Q&A session to key in your questions, or you can key in along the way while they are presenting, or simply use the raise hand button for an opportunity to actually ask questions. So let's open the floor for questions.
So I firstly would like to, I think it's a super meaningful project. The first question goes to the material performance because it's kind of a plastic, right? Wooden plastic. So I want to know when you measure the performance of the material, because it's the different layers of material attached to each other. For example, the pattern is attached to each other layer by layer. So how about the performance in between different prototype, this prototype? Is there any special test on this kind of a material performance? How they can touch each other and not broken by shear forces?
Thank you, Philip. That's a very relevant question. So for that, maybe first to say that in the simulation tool that we developed, we incorporated the material parameters or the material values that you can research online. And but still, as you say, it's not that simple. It's somehow depends on the bonding between the layers. So we did some physical tests, only 2, unfortunately, but if we had more time, we would have done more. So with different densities and somehow loaded them. On this slide, you can see this test. So we put weight on it and measured the displacement, and this informed the simulation that we developed.
To in large scale, how about you're making like a dome in London Museum? So what do you think when you enlarge this kind of pattern in the future as a part of the structure?
Yeah, definitely for us, research has to be done in the structural capacity of this system. But in our case, we explore in a more conceptual level. But yeah, further research has to be done in that topic.
Yeah, unfortunately, this was the only large-scale test that we could make due to the pandemic. But ideally, many tests like this would be iterated, and then we would get like a better understanding of how stable and how reliable these structures are for the architectural applications.
Yeah, and also the fixing strategies that we briefly touched upon are important when we talk about scaling up more and about actual applications to make it like the end shape structurally valuable.
It's a very good research. Thanks for your presentation.
Thank you.
Thank you. And are there further questions from the audience or the panel? Okay, if there's no more questions, thank you very much for a wonderful presentation and research. Now our second presentation comes from a group of researchers from CETA, INSAT, and the University of Copenhagen. And I think Areli, right? Areli Moss will be presenting today for their very inspiring work on 3D printing, bioluminescence for architectural materiality. Now the floor is yours, Areli.
Thank you. Let's see if it's sharing the screen properly. Full scale would be better. Here we go. Is it good for you?
Yeah, we can see the screen and we can hear your voice. So okay, take it away.
Perfect. So hi, my name is Verly Mosse, and I have the pleasure to introduce you to the Imprimer la Lumière project, which translates as printing light. It's a collaboration between the Center for IT and Architecture, which is based in the Royal Danish Academy in Copenhagen, and the Soft Matters Research Group that I have the pleasure to co-lead in ENSAD Lab, which is a research lab of École des Arts Déco in Paris. And our project is all about exploring the use of light-emitting bacteria as an architectural materiality shaped by 3D printing. So here, bioluminescence is used as means to question the critical thinking and the appropriation of bacteria as an architectural material and how this is changing the practice of architectural design and fabrication. So as most of you probably know, bioluminescence is a chemical form of light, which is produced by many marine organisms, some insects, and also some mushrooms. And it is commonly used in biology and medicine as a marker. In an architectural and design context is relatively underexplored territory of investigation, where it is used to imagine and probe more sustainable ways of lighting. So successful experiments in this area actually focused more on bioluminescent algae, and our proposal is really extending this research in the area of bioluminescent bacteria. And we use it, as I said, to examine the metabolism of a living architecture. So with sustainable agenda in mind, we are interested in a set of questions like what are the conceptual material, technological framework for bio-based architecture? How does designing for living system challenge our current models of design, registration, specification, fabrication, and inhabitation? Also, how does living and nurturing become part of a new vocabulary for how we build? So the project is revolving around a set of 3D printed self-illuminating structure that you can see here, like some early stages with different configuration. And this microarchitecture are really acting as design probes. So the point is really to reflect on how we can actualize an architecture, or the idea of architecture as a host for an ecology of species and symbiotic coexistence. So as a conceptual experiment, it is there to probe speculative inquiry or narratives addressing the implication of such a future that we expect to be desirable. And the material probe is really a role to explore the crafts, the materials, and the techniques through which this cultural pattern can be shaped, as well as to test, of course, the performance as an architectural materiality. So we made the choice to obviously tackle it from a bio-design approach, where ethical consideration are really becoming an interesting part of the research project. So of course, as a part of this, bacteria do die in the process, but they are also nurtured and invested into a new habitat. So we decided to work more specifically with a biosafety level 1 bacteria called the Vibrio fish curry, which is really used as a model in biology. And so it's a bacteria that is not genetically modified, that do not pose any danger to their surrounding, and that is fully biodegradable. So by using Vibrio fish curry in this design, we obviously delocalize the marine bacteria to a new host environment. And so this is, we provide a monoculture environment which both optimizes its living condition, but also make it less resilient to change. But designing with bacteria here means really for us designing for and with the life cycles of the living organisms. And you can see here, I can evolve, the light can evolve through the days. But let's jump to the fabrication process beyond the project. So there's really 2 aspects to the project at the moment, looking at how we can appropriate technique of growth for the bacteria. And also developing the technology for 3D printing the extrusion of the medium. So we used collaborative robots that you can see on the left part of the slide with a bespoke micro dispenser for extruding the medium. In the next stage, we use a digital model to compute the access path for the robot, and then we extrude the medium and inoculate the bacteria to get the illumination. We really developed this bespoke extruding system. The interest is that it allows us to address an architectural scale of fabrication, which is distinct from the traditional bioprinter that are operating at lower scale. The interest is also that it allows us to interface with programmable design environments for a higher degree of control and steering of both the design process and the fabrication one. The key part of this experiment is really to investigate how the topology and the surface treatment can drive the life cycles and therefore the light performance of the bacteria. So the first task was really about how do we 3D print the medium. So we developed a specific recipe to control the rheological property of the medium. So the medium here is based on a mix of agar, gelatin, nutritive media, of course, and some water. And really the key point was to find the balance between the need of a relatively important viscosity so we could 3D print, but also fast gelation stage after extrusion so we can build firm structure, but also structure that develop in high. So for that reason, we used actually household agar rather than a lab grade agarose. And a critical also point at this stage is the need to keep the medium at a constant temperature, which is here around 40 degrees. So we actually developed a self-regulating heating unit that you could see on the previous slide. But so our interest was really to sculpt this medium so that it can perform both as a scaffold and also as a nutrition for the bacteria. So we developed strategy for containing walls that allow both the dispersion of the nutrition and the oxygen. What was key to the design is having a high surface to volume ratio. So the bacteria is better exposed to oxygen and that it propagates better over the structure. So adding large surfaces and also interior cavities and also to build high was important to the process. But beyond the physical, it was also central to the evaluation process to develop a sort of metabolism tracking. So to do so, we used 2 stages, observation and oxygen sensing. So the first part was really developing imaging to register the bacteria growth and its propagation patterns across the surface in time. So it's the first line of picture, of course, that have been taken into darkness so we could visualize properly this evolution through time, but also used some oxygen sensing based on the dynamic quenching of oxygen sensitive indicator dye by oxygen to actually validate our hypothesis that oxygen would deplete gradually from the medium through time and through the growth of the colony, which we'd made obvious by working with the University of Copenhagen on that specific point. But we also developed digital models to understand the life cycle of the bacteria. So here you can see digital simulation that are based on a simple particle engine principle to approximate the printed geometry, which was developed by more specifically by my colleagues in Denmark. And the simulation here is the simulation of a propagation speed and life space that is calibrated using the observed imaging data from the physical probes that you've seen before. So we have a specific observation, like of course the light starts at the inoculation point, becomes most visible around days 2 and 3, and then is propagating around the surface over about 12 days. But I think it's more effective probably to share you hopefully the video of these experiments. So here you can see our living microarchitecture evolving through time. I'm presenting here one of the most effective structure, which is based on a spiral geometry that really allows us to channel and steer the light behavior within space. And I'd like to show you also next experiments where we're building on this spiral geometry, but allowing to go higher in terms of height. And you can clearly see that depending on the geometry, the thickness of the spiral, the height, then we got different type of illumination. So I'd just like to conclude by reflecting on perhaps the next steps of the project. So, and why we are also doing that is like to really truly enable the integration of living system into design. We really believe that new models are needed for design integrating the capturing, the characterizing and predicting of the living performance of organisms and their interaction with their environment. So we need to develop new practices that are based on temporal representation, so we understand how design can impact propagation and lifespan. So I hope we gave you already some first tips on how to do that, and we are of course continuing the journey further on this project. So I invite you to follow up what we do on both of our websites here. And I'd like also to thank the whole team, because it's not a solo project, it's really a collective dynamic across Denmark and France. So thank you very much for your attention.
Thank you very much for your presentation, Orly. And I think it's a very inspiring way to rethink the materiality of architecture through biology. Now we're open for questions from the panel or the audience. Aurelia, I have a question of my own. In the presentation, you sort of interpreted architecture as a hosting structure for organisms. And it's very interesting to notice the sort of parallel phrasing between the phrases used in sort of anthropocentric architecture, which we used culture, but then you also used culture to develop this sort of, to count the sort of group of bacteria. In that sense, do you actually see a scalar effect between the experiments at a micro scale, and sort of can it actually inform what we build or how we build? Is there a sort of analogy between bacteria and sort of how we live? And that would be my question about scale.
I'm not sure I got the question right. Do you mean like how we can scale up the materiality of the project? Or
how does it actually inform how we build for humans?
Well, I think a central point of the project is for us to really learn about this kind of invisible organism, and I can already feel it's affecting the way we ourselves engage with this kind of micro materiality. So I would expect it as an impact at a bigger scale at later stage as well. But it's opening a new type of sensitivity to time, I think, which is really critical, and also a sense of caring that is at least not in that way traditional in architecture.
Thank you very much. Are there any more questions or comments from the panel? Okay, if there's no more question, then we shall move to our third presentation from a team of ICD, MIT, and out of Ibanez University, who will be presenting or addressing their comparative study in matching digital fabrication and natural grown resources for resource efficient structures. So whenever you're ready, you can share the screen and take it away. So do we have members of the Di-terial team here? Felix Amsberg, Kathleen Mueller, and Felix Raspel? Okay, let's see if they are going to show up later. Why don't we move on to the next lecture? If if they're not here yet. Our next paper will be from Hao Wu from Tongji University, presenting their team's research on robotic motion planning with regards to obstacle avoidance. The paper's title is Application of Six-Stop Robot Motion Planning in Fabrication. Is it Ming Lu presenting?
Yes.
Okay, the floor is yours whenever you're ready.
Can I share my screen?
Yes, go ahead.
Hi everyone, good evening. I am Yimeng and will be a student in Tongji University. The title of our paper is Application of 6 Degrees of Freedom, Robot Motion Planning in Fabrication. With increasing variety of architectural forms, more and more building construction need to rely on the assistance of machines or robots. Since most of these projects are built on-site, robot obstacle avoidance in robot motion planning need to be considered. Robot motion planning is a long-standing problem that is still being studied today. In on-site construction environments, we need to find a balance between computational efficiency and reliability. Typically, the algorithms for motion planning are divided into sample point base and potential field base. There are 2 red points. One is the starting point. The other is the end point. In sample point based algorithm, several points are selected randomly. These points are called sample points. Then the algorithm searches for neighboring sample points around each sample point and draw a line to connect them. Then we can use other algorithms to find the shortest routes. In potential field-based algorithms, the green points means obstacle. A potential field is formed by the obstacle. This field can exert a repulsive force on the robots. There are also 2 red points. One is starting point. The other is the target point. These 2 points forms another potential field that exerts attractive force on the robots. The advantage of the potential field method is that it can be calculated very fast. It is possible to be used in real time. But in 6 degrees of freedom robots, the generated potential field is 7-dimensional, which means that it is almost impossible to be solved. So we use sample point-based algorithm in this project. PRM, which is a probabilistic roadmap, firstly creates a series of randomly different poles and eliminates those poles that collide with external objects and keeps the collision-free poles. Then it searches for neighboring sample points around each sample point and connects them. The connection of those 2 sample points can be added to the whole sample point map. Once all the sample points are connected, we use A* algorithm to find the shortest route. The mesh-to-mesh collision detection in Rhino is always time-consuming, so the method needs to be simplified. The robot arms are simplified to simple geometry, such as cylinder or spheres. Then these basic geometry objects can be used for collision detection. It can greatly improve the detection efficiency. The shortest path generated by the A-star algorithm is not a smooth path, so it should be smoothed. We can use Reynolds spline curves or a polynomial least square fit to smooth it. Then we compare the results from these two smooth methods. It shows that polynomial is better. It can ensure that the robot's starting and the final joint speed are 0. Besides, it can make sure that the values of the joint axis are consistent with the preset ones. On the contrary, when using Reynolds spline curve, the smoothed pose is always uncertain. Here is an example to briefly introduce the workflow on bricklaying. The robot is laying bricks and taking brick at the same time. If there is already an obstacle, then path planning is needed. But even if there is no obstacle, the height of the whole brick wall is constantly getting higher during the process of laying bricks. So it can also be considered as a changing obstacle. Of course, this is possible to write a program manually to follow the height of the brick wall, but this will definitely increase the workload of human, and it is also time-consuming. Here is a short video that shows a real-time motion planning in Grasshopper. The calculation time is short, maybe 1 or 2 seconds. By now, this function is available in a few robots in the latest version. If you are interested in it, you can download and try in for right now. Okay. For those formula and more details, you can read our paper if you are interested. Thank you for your attention. Hope you enjoy the CDRF conference. Thank you.
Thank you, Minglu. Thank you for the presentation, and thank you for and on the alternative method for robot route planning. And we can all agree that it's very significant in our actual practice of building, especially in situ with robotics. Now, do we have questions from the panel or the audience?
Yes, I do have a question. Thanks, Ming, for the presentation. I'm curious to see how your method compared to already existing approaches that are already in robotic fabrication, such as MoveIt or OMPL or RepX or other existing softwares. Like, of course, you had all the implementation done in Rhino, which is really nice, but how about the performance and speed in solving the problems? Does your solution always find, or does your approach always find a solution or no?
My paper is just do the application to the motion planning, and we use the method is already existence, and do some optimizing in Grasshopper, because Grasshopper is a little slow in computation. So we must do some optimization for efficiency. And the result is we realize the motion planning in Grasshopper. This, I think, is the one meaning for C.
All right, thanks.
Okay, are there further questions? So without further question, then let's move on and welcome our next presenter, who will be Mirko Daniluzzo, presenting from the UAE. The research is on the design of staircases for additive manufacturing. Mirko, please, if you're ready, go ahead and get started.
So I'm trying to share the screen.
If you can click that share screen button in the middle.
Is asking actually who can share.
And yes, you have the you should be able to have the privilege. I mean, we've opened it up for you.
I'll try again, but okay, now second. Yes. Okay, here we are. If you want. Okay. So hello everyone, my name is Michele, Mirko here, and we are founders of Nixo Studio, Architecture and Product Design Practice. We love to define Nixo as a shape-shifting practice, a team that focuses on the articulation and management of integrated scenarios, both in the design and fabrication processes. So we will introduce you to an ongoing project focusing on the application of additive manufacturing technologies for the design of staircases. So let's start that. We believe that additive digital fabrication allows architects to reinvestigate material processes and creates new design opportunities to explore novel aesthetical and functional expressions in architecture. As in our case, enabling reinterpretation of the topology of the staircase through the use of thermoplastic materials. So the research focuses on the prefabrication of components for many reasons, like the possibility to intervene in buildings restorations, or also because in the majority of cases in residential buildings, masonry or concrete staircases are, let's say, limiting the interiors configuration, so are kind of left as an autonomous component in the design of interiors. So the market of the interior non-standard staircases, leaving aside the in situ concrete stairs, goes mainly in two directions. So the first one is custom-made products, and second is in-kit products. So the first case is generally defined by a specific design that is adapted to the context in every single component, making this one one of the main factors that rise the prices of these products. The in-kit products are instead meant to be mass manufactured to reduce the design and manufacturing costs. In this staircase typology, the adaptability is shifted from the design phase to the assembly. The interaction between the standardized components is designed to guarantee a range of configurations. The disadvantage of this is that it's difficult to achieve an aesthetical result that seems designed for a specific case. And usually these products are manifesting this adaptation with discontinuities. So additive manufacturing could bridge these two typologies with an affordable on-demand customization, customized fabrication, creating staircases that can adapt to a specific context without losing the overall aesthetic quality. So the advantages of using 3D printing for such products for interiors of medium-scale architecture components can be listed as follows. And I will just jump so you can just simply read what are the advantages. So let's say that in our case, the staircase is thought of since the beginning as a discrete object. So where each unit has the size of a furniture piece. This analogy helped to channel the characteristic of a unit as a lightweight object, something mobile, easy to handle as a single piece. So 3D printing is used to build the entire body of the module in an integrated way to avoid any additional component. This analysis suggests avoiding using material with a very high unit weight like concrete, but still capable of decent tensile and compressive strength. So yeah, non-standard stairs have an important role in architecture, but their complex detail pose significant fabrication challenges. And one of the preferred material for custom stairs is steel, which can be shaped in different ways, but still cause logistic issues, assembling problems, and high number of components. So 3D printing can unlock an entirely new vocabulary of shapes previously not available with traditional systems and materials like steel, wood, or concrete. Only a minimal amount of 3D printed plastic is required actually to deliver a very thin, stable shell. So complex topologies can be achieved with less effort. Such elements can be optimized to the structural performance or improve functional aspects, as well as introduce a radically different aesthetic. So one of the first goals considered in the design process of the staircase was the reduction of the components to speed up and simplify the assembly operation. And as a direct consequence, the reduction of the suppliers chain. The module incorporates the riser, thread, and stringer in one single element. And this logic makes the module lightweight, easy to transport again, and quick to install. The connection between each module is guaranteed by standard mechanical hardware employable for every size and every configuration. So in synthesis, the characteristics used to drive the design process are integrating the components, have a lightweight piece, be easy to assembly, quick for manufacturing, and one of the most important, let's say, the adaptability to specific configuration, maintaining, let's call it this way, an organic wall aesthetic. So for structure integrity and to the use of FGF technology, the module, which is a single step, is described as an open volume or a reverse base, which with action that allows a continuous printing path. The step is then a hollow volume where the mechanical stress is handled by twisted surfaces operating as struts due to their triangular configuration. The dynamic section of the single module is designed to optimize the printing time while guaranteeing the required mechanical strength. The adaptability is reached through the definition of a parametric model of the module. So the adjustments of the module affects the production costs only in the quantity of material that is used. So initially we developed an oblique type of interlocking between each module, which you can see here. Then we simplified into a horizontal stacking configuration of the components, relying on mechanical fasteners to allow the possibility of an easy assembly and disassembly of the staircase. So to maximize the mechanical performance of the module, the extremities are based on triangular shapes. The linear connection between the two sections is expanded on the back to form an arc. This arc defines the boundary surface of connection between the modules. The outer surface of the module is simply the interpolation of the rise thread and the curved surface of the back. The analysis of the sections reveals the transition from a triangle shape to a trapezoidal one in the middle section. The inner surface traces the triangular shape on one side to then interpolate to the riser profile on the opposite side. This allows having one side that is closed and the other open to insert the fastening for the mechanical connections and inspections. So for instance, from one side of the staircase, you would not see any mechanical fasteners. So for the spiral version, the open side is the inner one, where the triangle is smaller. The articulation of the inner surface is necessary to reinforce the structural integrity of the wall step. The flat surface of the thread is indeed larger and needs a struts to avoid flexions under payloads. The inner shell is so used to generate two surfaces that are reinforcing the thread. The area between the two curves has a double layer, but the loads are distributed down to the base of the step. So the promising results of these initial verifications opened the possibility for a more accurate series of testing to verify inflections, breaking loads, and the testing of an entire staircase following the global standards requirements. So this will be the next step, which is in schedule for this summer. So yeah, this research proposes an approach to FGF design that balances process efficiency with a strong design focus, aiming to articulate a performative and yet unique aesthetical quality for staircase design. The combination of BREP design and additive manufacturing possesses a wide range of architectural qualities that have to be explored and that have to be explored and have the potential to radically change the design and the construction processes, so the language and identity of contemporary architecture with functional hollow surfaces. After this first phase of testing that demonstrates the viability and sets a reference point, much further research has to be done on points like structural and mechanical stability, material life, fire resistance, the toxic effects of material, and so on. In particular, regarding the material printing process, the opportunity are open to exploring other recycled materials or bioplastics. And another study concerns the adoption of TCM processes using robotic arm-based printing systems, especially in the case of spiral staircases. And at last, new fabrication methods suggest also the definition of custom computational tools embedding the printing and material properties. So here you can see a short video of the load of a single module in which, sorry for the quality, is a bit rough, but still it's nice to see it. And we applied the load to the single module, so the single step of 500 kilos. So let's say that we are quite happy of this result. And yeah, the next step is to test the entire staircase and with the global standards, and we'll see what will happen. We cross our fingers. So yeah, thank you for listening and for watching. Hope you enjoyed our research.
Thank you very much. We did. Shall we actually open the floor for questions from the panel and the audience? And to kickstart, I think there's an interesting sort of dilemma that you faced comparing the two projects when you transferred from a geometry-based solution for the connection to standard fasteners. Then to me, I was curious about your attitude to, or your stand towards such tectonics in your future research. Do you think that additive manufacturing should address sort of the tectonic level by sort of its geometric possibilities, or do you think that we should keep a line between 3D printed parts and the standard fasteners? Is there a line there?
It's an interesting question because it's also what we. It's precisely the process that we went through, in the sense that at the beginning we were fascinated to find let's say an interesting way to connect, and also efficient way to connect without any, let's say, external fastener. And we were thinking about gluing the pieces all together, so to have another, let's say, bonding technique. The point is that facing the market, let's say, and let's say to be more close to what are the needs, let's say, of the market, and also the fact of being able to disassemble the staircase in case if necessary. So lead us to kind of, okay, it's better maybe to start with a situation where we have, let's say, a standardized connection system, and then eventually we can move to the other direction later on. So to revert a little bit the ideation process.
Sure, thank you. Do we have more questions from the panel and the audience? Okay, thank you, Mirko and Michelle. Let's move on to our next presentation. I think it's Ayub Lachi from CETA is going to introduce a descriptive modeling tool for timber structure joint design. Ayub, once Mirko and Michelle stopped sharing the screen, the floor will be open to you, and you can take it away whenever you're ready.
Yes.
Mirko, can you stop sharing so that I can share my screen? Okay.
Awesome. Okay, I did it. That's fine.
Yeah.
Okay.
Awesome. All right. Can you see my screen?
Yes, we can see your screen and we can hear it clearly.
Amazing. Hello everybody from Copenhagen. My name is Ayub Al-Harshi. I'm a research associate here at the Center of Information Technology and Architecture at the Royal Danish Academy. And I am here on behalf of my co-authors, Mette Ramsgaard-Thomsen and Martin Tamke. And I'll be presenting to you our paper entitled Joint Descriptive Modeling, short for JDM, for assembly-aware timber structure design. So this paper introduced a novel approach for timber joint design that embed both fabrication and assembly consideration within the same model to avoid mistakes that might cause delay and further expenses. So going back a little bit to the start, with the rapid advances of computer-assisted design tools and parametric modeling in architecture, designing and manufacturing and assembling building with complex geometry is becoming more and more accessible. And that is especially the case within the timber construction field. And simultaneously, we noticed that digital fabrication machine proliferation is pushing toward an uninterrupted chain from design to fabrication process. So now we can have complex structure described as an exhaustive parametric model, and we can break down all that complexity into several separated relatively small elements that can become more manageable. However, while this parametric model can provide an extensive overview of the design, this seamless translation from design to fabrication I just talked about to assembly is still very limited to academic field, where the global design parameters are known in advance. As actually it is the case. In large-scale projects, it's very difficult, if not impossible, to have an overview of the different component fabrication techniques and logistic consideration. And so all these parameters remain unknown in the early design phase. So to attempt solving these problems, we've looked at practice in other disciplines. And the popular approach is design for X, which is a philosophy that has been around now so far for several decades, and it aims in general to ensure the quality of products and services, and at the same time to optimize the manufacturing procedure. So D for X, or design for X, is a generic term where the X stands for any critical consideration during the design that would affect the outcome. For example, we can have design for manufacturing, design for assembly, design for disassembly, design for testability, maintenance, and so on. But here I would like to focus on two elements, which are design for manufacture and design for assembly. So mainly design for manufacture is pretty much looking at the optimization of methods and procedure for making or fabricating individual parts, while design for assembly is concerned with how these parts that you just manufactured are put together to constitute a final product. And most products are complex and constitute of several intricate elements. So these two disciplines are merged together, DFA and DFM, and constitute design for manufacture and assembly. And recently, there's been a lot of interest from researchers to look into application of design for manufacture and assembly in architecture. And while it is present to some degree, I would still argue that it is yet to be implemented efficiently. And I would even further claim that such approach would particularly be beneficial in timber construction, where it is essential to deal with both fabrication processes and on and off site assembly strategies. So moving on now to the core topic, timber structures are usually composed of multiple elements that are put together either on-site or off-site with or without additional fasteners. And it is essential for us to think about the connection between these elements. So for the purpose of this research, we distinguish between two types of joints. We have integral joints that can be connected without the need of any additional fastener, and joined with fastener that would actually need an additional element to be assembled, let it be metal plates, bolts, screws, or whatever. And while these two types of joint require different design approaches, they are fundamentally the same thing. So they both need extensive planning and for fabrication and assembly. And within the scope of this work, we will be focusing exclusively on integral joints, so joints that can be connected without the need of any additional elements. So this research is actually building upon previous work that's been done about design for assembly in architectural context. This research was developed as an extension to an existing framework, assembly information modeling, which was developed by us previously. And so Assembly Information Modeling, or AIM, is a digital framework that is designed to integrate assembly consideration into the design process. So based on principles from Design for Assembly, it aims to include all the necessary data to describe precisely an assembly sequence that would include geometry, direction, sequence, environment, and so on. And the flexibility of this model allows so many applications that have been demonstrated before, such as cloud collaboration or augmented reality assisted assembly, robotic fabrication, and so on. So there are many methods, actually, if you look out there, how to that are suggested how to exchange fabrication data within the timber industry. And this is achieved exceptionally, we think, by the Build and Transfer Language Initiative. So Build and Transfer Language, or short BTL, is an open standard which provides a parametric description of the geometry of a timber building component. So an important thing to note here is that BTL is purposely not machine specific, and processing is defined through the result rather than the actual machining process. So no matter what machine you're actually using to fabricate the joint, you can, as long as you have a compatible BTL reader, you can convert it to machine code. So here we classify the machining methods in timber into 3 categories. First, we have task-specific machines, and these are machines that are capable of doing one unique task with a high accuracy and repeatability, drilling, cutting, and so on. 2D/2.5D CNC routers. So these are the common routers that you find in every shop. Usually, you just need a 2D drawing as an input, and these machines can do contouring, surfacing, drilling, and so on. And finally, generic multi-axis machines, and that would also include industrial robotic arms. And these machines are capable of milling or cutting complex joint and run several consecutive operations with different tools. So to include a support or to support exporting machining operation in our approach, we considered the DXF format, so the Autodesk Drone Exchange format for task-specific and 2D and 2D.5 CNC operation. And all other machining operations are exported using the BTL that I just presented earlier. So what we do here is essentially we focus on a smooth functioning and seamless workflow. And we try to achieve a multi-scalar and multi-level of detail going from the initial design to detailing to the actual fabrication data. And of course, we keep going toward the goal of the research, which is to provide a base for designers to facilitate the design of timber structure. So what we do is we try to provide a joint catalog for the designer that they can use, and then they can generate automatically joints that you already know that they are assemblable and fabricable. So the node in the structure can be replaced with the joints, and again, these joints are already enriched with fabrication and assembly data. And this joint can be generated automatically from a minimal input. So you just need direction curves and intersections. Of course, we have the joint catalog, which is used within the parametric model. The joint can be adapted into the structure to incorporate various limitations, such as maximum angles, minimum sizes of stock material. You can also, the user can also specify nodes within the structure that's according to some design or aesthetic preferences. Obviously, the export of BTL, NC, or DXF for fabrication, which is included in the assembly model, is automated as well. So looking a little bit under the hood, what the computational engine that we developed is doing essentially is just looking at the intersection and analyzing the connection for potential conflicts of or collision, and then evaluating the joint direction, and then look at the joint database that we provide for a compatible joint and at specific stock material, and then suggest a joint model. And upon validation by the user, it's all the previously mentioned data, fabrication, assembly, and whatever is automatically generated. And an ADM file is also generated, which can leverage the capability of the assembly modeling framework presented earlier. So the proposed implementation for our GDM is demonstrated on the Rhinoceros 3D modeling software. So we have a first part of GDM core, which analyzes the intersection and structures and capable of generating the joint geometry. And the second part, which analyzes the geometric features of the say joint and generates corresponding BTL file. For the generation of BTL file, we relied on the Grasshopper plugin Woodpecker. And we had to go through a little workaround as there is no API exposed by it. So we used intermediary interface exposed by Grasshopper, which is the Grasshopper Python lib components. And that allowed us to have a direct interaction and scripting with the plugin. And for the rest, we just used the default Rhino programming API. So zooming back a little bit to summarize what we did is actually we have all the global geometry or the joined information and the geometric features that are fed into our GDL plugin. That is actually exporting the assembly direction, analyzing it, of course, and then exporting the assembly directions for assembly simulation and the fabrication data for CAM software. So as an overview, we think that the outcome of this work is a novel joint representation that focuses on timber construction. We believe that this representation would allow embedding both assembly and fabrication consideration into one single model, which is the novelty of our research. And we think that the implementation of the method within a CAD software is also offering a tool for designers to iterate rather quickly over different design options and have very realistic expectations about the fabrication and assembly to assess their design choices. Further steps would be, we would like at least to extend the joint catalog, add more variety for it, and also add support for other type of joints, such as joints with fasteners. And we also think that an integration with other CAD software would enable even a higher degree of iteration freedom. I believe that will be the end of my presentation. If you have any questions, please come. I'll be happy to answer.
Thank you for the presentation. Now the floor is open for questions.
Hi. Well, it's a very interesting research, and actually when we play with timber, robotic timber construction, it's really important to integrate the design process to the fabrication. I think it's a very meaningful research, analyze the transformation of especially different files and how to integrate them together more efficiency. And normally speaking, I think this kind of, we name it as kind of Chinese drawings with no news, it's cutting together. We make a lot of research from furniture, Asian furniture here, and which really, geometry really complicated. Sometimes it's interlock to each other, triple layers, one lock another layer by layer. So it's not only about the form, but also the precision and the logic, how to put them together should be accurately controlled by the robotics. So, I mean, the question goes to your implement the whole process from C# to Rhino, Grasshopper. What we are doing actually right now is we try to simplify the whole process, because the designer, not every designer can easily write the code of C# or Python. So we try to develop some easy plugin to just some Grasshopper plugin, and which will help the unprofessional or some designers that easily control the robotics. So I don't know what's your vision in CETA to set up this kind of working flow and how to collaborate with the architecture, design, and profession, and also collaborate with the industry. So how would you like to ask your
Yeah, thanks, Philip, for the comment and the question. Actually, I totally agree with you. It's always hard to find this, to find a designer who is actually capable of writing code. And we are rather a small community here that get together, and that we are rather designers that do programming. And so for my code, what I did actually is we developed the whole computational engine in C#, but the final user does not have necessarily to deal with what is under the hood. So so we offer, of course, a relatively easy platform that you can just, I would call it, point and click to generate all the joints, and all the work which is under it is already done. And that was actually one of my closing remarks, is that I would love to see this kind of works extended to other softwares, not only Rhino, because even if a lot of Rhino is widely adopted, not many people know how to use Grasshopper. I would love to see similar stuff in Revit, in ArchiCAD, in AutoCAD maybe, so in the software that everybody can use, and so that we can push forward this thinking of assembly and fabrication in the very early phases. Yeah, thanks.
I have a question, technical question for you. Are you right now? We saw that the code that you're developing is mostly based on the sort of convexing and of geometries. That's sort of thinking about coplanar joints for majorly sticks, right? Yeah. Are you actually planning to develop this, or the code for, first of all, to spatial joints of wood, and second, to incorporate right now, because it's majorly based on geometry, but are you planning to extend it to, for example, incorporate standard fasteners or materials other than wood to help the timber joints?
I think that is a very ambitious approach. Yes, of course, I would love to have an approach that would work for everything. But of course, for the purpose of this research, we're limited to timber and to this type of, or this typology of joints. Yes, it is very hard for us to, or at least I think it's very hard to find language that would describe every joint in a way that would be, that is necessary for it to be automatically generated. That's why we propose, even if we propose a certain number of joints, we are trying to, or we or anybody, and we invite everybody to come and try to think with us, how can I describe a joint with very limited design vocabulary that we have. So yeah, I think that would be the next step for this research.
Thank you very much, Ayub. Are there any further questions? So without further questions, now it is our time for our last presentation of this session and also of the day by Bala Murali Kumar, Yunchun Xue, Zhuoyang Xing, and Dan Luo from the University of Queensland. They will be presenting their paper titled Process and Evaluation of Automated Robotic Fabrication System for In-situ Structure Confinement. Please go ahead whenever you are ready.
Can you see my screen?
I think you just canceled it. Yeah. Now we're seeing your screen.
Greetings. So my name is Bala Kumar, and I'm doing my Master's of Engineering in University of Queensland. So the project is Process and Evaluation of Automated Robotic Fabrication System for In-situ Structure Confinement. I'm representing my teammates Zuyang Chen, Jose, and Dr. Dan Lu from Department of Architecture. So the Sagrada Familia, as everyone is more familiar, it was.
Yeah.
I'm sorry. Can you hear me?
Yes, we can.
Mit dem Video. Weil es irgendwie hat angefangen zu rendern.
Nice.
Yeah, go ahead.
Is the video also available? Is my screen share?
Your screen share is fine.
So the Sagrada Familia church in Spain was proposed and constructed in 1892, but the construction still hasn't finished, and it's because of the columns that are on the structures, which are mostly tree-like structures, which are very difficult to construct as well, even with today's modern fabrication techniques. And on the right-hand side, you can see the hybrid double-skin tubular arch bridge system developed in University of Queensland. It's a composite structure where the fabrication and assembly of the structure till date is a difficult process. And then we have, in theory and in simulation, we can develop most efficient and modern bridge structures by using Bezos algorithm developed by RMIT University. So when we translate from the modeling technique to the fabrication system, the current reliability method is 3D concrete printing. And so the conventional concrete casting and steel manufacturing process is highly efficient and less time consuming for standard cross sections, but they have limitations on the irregular shapes and sizes. So additive manufacturing, on the other hand, is very flexible and effectiveness for fabricating customized parts with complex geometries. These techniques are used in various industries to create physical prototypes, even in the conceptual stage of the design itself. So the construction industry has started to adopt the 3D printing process, but still it's still in the it's still not yet developed fully to manufacture non-standard cross sections. So this gives an issue where it becomes hectic to transport the cross sections and then place it on a site installation. So the big disadvantages of these are the logistical nightmare of fabricating in a site A and then transferring it to a site B and then erecting it there. So the major disadvantages are the logistics, the extra machinery involved in fabricating the machines and installing it on site, and it will cost huge expensive if the project gets delayed. So the alternative method of what we thought was to do a composite structure, which is more material efficient and is also structurally performance based on the hybrid double hybrid structure developed here. So the methodology is to use fiber reinforced polymer fabric to fabricate a formwork and then transport the formwork to the site and then install it there and then cast concrete for both standard and non-standard cross section. So the methodology that we adopted here was to design in Rhino environment and then extract the geometry surface information and then use the path planning method with KUKA robot and then start the fabrication process. So in the fabrication process, we use epoxy resin to form as an adhesive, and then we use for curing for quicker curing, we use heat gun, and then we just demold it from the fabrication side. So the KUKA robot, which is involved here, is shown here. So the first part will be the end effector. The end effector consists of the support rollers, which is mounted on the aluminum steel frame, and with that springs, and then which has springs on the sides, so that it can apply adequate pressure against each other and maintain their spatial position during the fabrication process. The FRP weave will be strategically positioned between these two rollers, and the hollow geometry could be maintained by the pressure as the rollers are passively driven. The guiding roller is responsible for the smooth transition from the FRP fabric roll to a straight fabric while maintaining the tension to prevent the wrinkles in the additive layers. So the material properties we used here are the commercial FRP fabric, which is 150 mm in height, and installed directly onto the support holder without any pre-processing requirement. So FRP fabric needs to bond together. So we use the epoxy resin, which with a hardener and a primer at in a ratio of 100:40, which is prescribed by the manufacturer. So the working time of for the epoxy resin is only 15 minutes, beyond which the epoxy resin starts curing by exhibiting exothermic reactions. The curing time of the adhesive for the FRP fabric was different. The epoxy resin, when applied to fibers, took approximately 90 minutes to 120 minutes to completely cure. However, it was found that the external heating apparatus, such as when a heating gun is used at 200 degrees Celsius, we can cure the epoxy resin in just 20 minutes. So the surface of the geometry, which is extracted and then used for path planning algorithm, is used in the fabrication process. The end effector is installed in the robot 6-axis hand and tested. The fabrication process follows a spiral path, and hence the data configuration file was set for the robot 6th arm, which is more than 360 degrees in rotation. So from experience, it is suggested that the generated path planning script is verified by allowing the robot to run without any fabric and epoxy resin. After the successful completion of the dry run, the epoxy resin is used with the fabric. So here on the left, you can see that we designed the cooker robot and the modeling, which is shown in a GIF image. But in reality, it takes a very long time to apply the epoxy, and then again, so here it takes a very long time, and it takes around 20 seconds to go from one end to another end, which is like a length of 45 degrees along the perimeter of the surface. So we conducted initial trials. So the trial 1 and trial 2 as shown here. So from these two trials, we learned what are the influencing parameters and we observed what factors we need to control so that we can get good trials on this. So on the right, there are like two tables. So the fabrication procedure is shown on the table 1. So first, we mix the epoxy resin, and based on the number of layers, like whether it's 10, 5, or 2 layers per hour as programmed in Rhino or Grasshopper environment, and then we apply the resin and we wait for a specific time. So after we wait, we then rotate the robot to a 45-degree length, and then we again start applying the resin. So we repeat the process for 2.5 layers, and then we start applying heat gun for a fixed number of durations. So repeating this again and again will give us the standard length and the height of the geometry. So after the initial prototypes, we fabricated a few as well in 10, 15, and 20 layers. So the information as given on the table here indicates how much hours it took and how long and what was the speed of the robot during the fabrication process. So the main influencing parameters in the robotic fabrication was the fabrication time, epoxy curing, and the fabrication speed. So the fabrication time, we calculated it by using these formulas. So, the main parameters that depend on the fabrication time are the robot winding time, the time that the epoxy takes to cure, and the total height of the prototype. And the velocity at which the robot is also winding the fabric. Epoxy curing time is influenced by two factors, namely the temperature and the number of layers. Now, any temperature above 200 degrees Celsius based on the material that we used actually started causing harm to it. So we had to limit ourselves to 200 degrees Celsius. Now, at 200 degrees Celsius and at every 2.5 revolutions, we applied heat for a duration of 30 minutes. The fabrication speed in general is affected by the curing time, layer winding speed, which in this experiment was limited to 1 centimeter per second. And then the area of the column covered by end effector in a single revolution. So these are the prototypes which were manufactured on the left. 3 different prototypes were initially fabricated, 10, 15, and 20. And the fabrication time that's listed here is 6, 10, and 14 hours, which is approximate because we had to stop in between and then continue it the next day. So this is the timeline of the fabrication process for each material. So after the prototypes were fabricated, we did a 3D scanning and we changed it into a point cloud system, which was then imported in the Rhino environment. So the pink color is a designed or proposed geometry, while the X indicate or X marks here, or the point clouds indicates the fabricated prototypes plan. So on the right, we have summarized our results, where for the deviation for 10 layers is 97%, and for 15 and 20 layers is approximately 98%. There's less deviation between 15 and 20 layers. So for further fabrication of higher order elements, we will be sticking to 15 layers. So as you can see here on the image on the left, when we start the fabrication, the end effector and the fabric that rolls through the rollers here are actually should be in tension, but because of the environmental factors and sometimes because of the already fabricated elements, they are not in tension. The major reasons will be because of the epoxy resin that is applied previous in the fabricated layers. And here, the red line, the blue line and the red line indicates the deviation of how the fabricated layer should be formed. Here, the fabric on the image on the right shows that because of the tension on the bottom and the less tension on the top, stretches the fabrication in a non-uniform layer, which causes the fabrication prototype to deviate from its original designed surface. So here, the image on the left shows that as you apply more epoxy glue, and when the end effector starts rotating in a clockwise direction, because of the tension, a part of the fabrication fabric starts rotating in counterclockwise and the other half starts in the anti-clockwise direction. And as a result, if the tension is very high, there is and the layer and the interlayer height is high or large, we can see an inward spiraling of the fabric as well. So these are some of the challenges that we faced during the fabrication process. So the major discussions from these fabrication is that the integration of emerging technologies of advanced fabrication between the architecture design and the structural engineering is possible. The major parameters that influenced the proposed additive process were identified and investigated in this experiment. From our current study, it is evident that the proposed additive process has the potential to bring a change in the fabricated structure component because of the strength, design, geometrical flexibility, cost effectiveness, while dealing the following disadvantages like fabrication time, manual epoxy resin application. Thus, further investigation of the methodology and technique to implement for large-scale, non-uniform and complex geometry by integrating the FRP and concrete is required. So we can conclude by saying that the material efficiency and structural performance can, with the current construction process, needs has to be tweaked. So this paper explores the feasibility of using the additive process of FRB dynamic winding formwork for concrete casting of customizable structure components in large-scale construction. The additive process proposed in this paper uses an FRP that is operated by QCAR robot with a customized end effector, and the epoxy resin is used as a adhesive for lamination in the process. 3 prototypes and 2 trial experiments were conducted to study the influential parameters, and the deviation of the fabricated components were recorded from the original proposed design. So the deviation was less than 4%, which indicates that the further research and thing is possible and is also required. Thank you for the opportunity.
Thank you, Bala, for presenting this very novel additive manufacturing method. Let's open the floor for discussion. Any questions from the audience? Yes, Professor Yuan.
Yes, I think it's an interesting research since when we make research on the 3D printing technology, not only ceramic material, but also in some different material like concrete, like welding, metal welding. We do a lot of this kind of research, but the approach of this one is totally different. I think they make another layers of the mold to try to control the 3D printing process. I think as a research paper is quite meaningful, but I still want to challenge the efficiency and feasibility of this control process. Since we want to predict the printing result, and we need to reading very carefully into the process. But actually, in the real situation, when we 3D printing, the material different times you put in the effector will every time I think the density and the humanity and also the proportion of the material is all different. It's really difficult time by times when you implement to predict what will happen, because the water percentage, for example, and also in the other situation is similar. We use 3D welding, metal welding. In the project, we find when we have 3 or 4 different effectors, every effector have different performance. So when you set up a training data toolbox, it's really need a lot of time to really to understand the behavior performance of each effector. So I mean, the first question goes to, I think it's ideal solution to predict and control the proposed geometry by this effector. But in the real situation, when you test the different mock-up, how many pieces you test, and do you think its prediction of the predicted proposed geometry is feasible, or do you have any question or problem or difficulty in the process of your printing?
Yes. So the deviation of the fabrication will depend upon the environment that the formwork is being printed on. And regarding the concrete casting, yes, it has a high uncertainty about the hydrostatic pressure the concrete will insert on the formwork. Further research as a next step of this project is about casting concrete on the formed formwork and testing its properties to have a good solid prediction, so that even in the inside, even if it is even when it is fabricated, the response to the loading is within the prediction limit.
Right, are there any more questions? Okay, thank you, Bala. I guess that's all for the presentations today. Before we end the session, there's one notice. That is for the presentation that we missed in the session, the D-material matching digital fabrication and natural grown resources for the development of resource efficient structures. This presentation, along with others, have been recorded, and so they will be uploaded to the official website of CDRF. So if you're interested in this presentation and others, see what you have missed, please check the official website for the presentation videos. And also congratulate every presenter and researcher. You've done quite a very interesting body of work. Professor Yuan, would you like to say some closing remarks before we head into the keynote speak?
Thanks. Thanks a lot to Xu chairing the session 4. It's great. Thanks for your work, and also congrats to all the presenter. I think all your research very interesting. I think most of you, the background from different research group and PhD, right now the PhD candidate or the researchers, professional researchers in these different research labs and universities. I think Digital Future gave a very interesting platform for the future researchers, including not only from Europe, but also States, Japan, China, and all of the world coming to this platform yearly. We have a CDRF, this is a third conference. And every year we're looking forward to a set of the proceedings of the papers. So this year we have a quite remarkable paper submission. More than 110 papers turning, and we have 30% of them, around 40 papers will be published on the proceedings of the CDRF Springer book, and all these papers will be open access. That means more people, a lot of people will freely read your paper. I think what we're doing, try to make promotion for the community and try to introduce the best researchers. Although you are young as a or research group, I think CDRF produced a special platform for you to the academic platform, and and secondly, I think after these proceedings, we'll select around 15 to 20 extended papers and publish a book followed by the special topic. And this year, the topic is material intelligence. So we're looking forward to invite some theorist or practitioner to write some theme papers. At the same time, we will select some of the best paper from proceedings to extending your paper and publish in the book by Springer. That's also open access. I think the culture of open access is learning from the other discipline. For example, IEEE, and they have their publication platform. And I think in architecture discipline will be very interestingly, not only in the robotic fabrication, but also computational design and environmental performance-based design and energy simulation and planning, prediction. All these topics will be interesting in the future. So it's a great welcome for all the researchers come to turn and participate to the platform CDRF and Digital Futures, and we try to produce a free educational culture in the community. So thanks a lot for your presentation. And I think after 2 minutes, we want to invite our last keynote speaker, Sandra Mannington and Matthias de Campo from University of Michigan to give us a keynote speech. So see you very soon in 2 minutes. Thanks to all the presenters and thanks to Xu Weishun chairing the session 4. Thanks a lot. I think we are in the same room, just waiting for Professor Matthias and Sandro to prepare for their presentation. See you very soon. So wait a moment, I want to make an introduction. Hi, Matthias. How are you? It should be really early morning, right?
Yeah, it's early. Not too early, but early. Yeah, that's okay.
6 o'clock, right? So thanks a lot for your coming. I think we have still 1 minute. And so how long will be the lecture today?
40 minutes.
Okay, I think we'll follow by some questions. Yeah,
it's good.
Great. And this morning, Chinese time, this morning we have Daniel Bodigan and Jules Rastin, who make really fantastic lectures, and looking forward you. I think Matthias play very important roles in the architecture, digital architecture research. Over the past few years, Matthias gave a lot of support to the DigitalFuture community. So it's a great honor for us to have him and Sandra here as well.
Okay. I think Sandra's video is blocked. Maybe somebody can unblock her so she can open her camera. There we are.
Hey, great. Hi, Sandra. How are you? So please create the keynote. I want to present Matthias and Sandra to the public. Can you create the poster? Okay, great. Okay, dear friends, dear Digital Futures friends, welcome back. So it's a great honor for us to invite our final keynote speaker today, and Matthias de Campo and Sandra Manninger coming to give us their lecture. So both of them are the old friends of DigitalFuture community. I think we can trace him back to around 7-8 years ago. Matthias came to join us and help us to set up this community. And year by year, and every summer, both of them traveling to Shanghai and teach at least 6 times of the workshops to all the students. And very specially, we can see the emergence of their research. It's extremely interesting from not fabrication, but also to some artificial intelligence and different technology scenarios implement in the workshops. So I want to introduce both of them. Matthias de Campo and Sandra Manninger are the founders of SPAN, which is a global architectural practice known for its application of contemporary technology within the design process. And Matthias and Sandra are the registered architect, design, and educator. And Matthias is an associate professor at Tubman College for Architecture and Urban Planning at the University of Michigan, as well as a director of architecture and AI lab, AR2I1, right? How to pronounce it, you can pronounce it later, which is a very interesting lab, collaborate with the robotic team from their school. who are focusing on the application of artificial intelligence in the field of architecture. He was awarded Accelerate at CERN Fellowship and the AIA Studio Prize, and was elected to the board of directors of Arcadia. Sandra, who co-founded SPAN with Matthias, is currently an assistant professor of practice at Taubman College of Architecture and Urban Planning at University of Michigan. She has also taught various institutions, including University of High Arts in Vienna and the Dessau Institute of Architecture, Tsinghua in Beijing, and Tongji in Shanghai as well. So I think both of them have a very pioneer thinking, especially recent years. Both of them focus on architecture intelligence, which have a profound influence to the architecture community. And that's why today we try to invite both of them make this lecture, is try to give Digital Future community very special remarks on the newly developed technology and research direction. So let's welcome Matthias and Sandra. The floor is yours, please.
Philip, first of all, thank you very much to the Digital Futures community and to you for your generous invitation. So I call this lecture Neural Architecture because I'm developing sort of like an idea of how this field, this emerging field, can be described. And I borrowed the term basically from the arts and music that are using generative adversarial networks and other AI techniques, who call their productions, for example, neural music or neural art. So I borrowed that for architecture. And for architecture, we have fared fairly well when we borrow things from the arts. Neural architecture is the field of architecture that is primarily preoccupied with interrogating the emergent field of artificial neural networks as a method of designing architecture. ANNs can be described in short as a sequence of mathematical algorithms which are capable of registering latent correlations in a set of data. The applied algorithms mimic certain aspects as of how the human brain operates. This position, however, is still highly disputed. As for now, and for the sake of this conversation, I would suggest agreeing that the algorithms at work in neural networks were inspired by the current knowledge about certain processes in the human brain, such as hallucinating and dreaming. In this sense, neural networks can be described as a system of neurons that can be either organic or artificial. These comprise elements of what can be described as artificial intelligence. So I run together with Sandra Manninger the architecture practice SPAN. And I also run the newly founded, so I'm the director of the Architecture and Artificial Intelligence Laboratory at Taubman College, which was founded recently in order to expand the research we've done in the last couple of years. And I would like to start maybe with a quick run on the origins of my own practice and my obsessions. So I've been occasionally being described as a member of the lineage of Phoenix architects obsessed with technology. However, this obsession is not one of understanding technology as a tool of expediency, but rather the interest is in the interrogation of the tool as an agent of culture. So similar to other architects in the Austrian history, such as Kopinoblau, Hausrucker, Hans Hollein. There's also an example here of Walter Pichler, not necessarily an architect, but certainly also within that sort of area of thinking. And that's exactly what I try to encapsulate with the projects I do together with my team. So the interrogation of contemporary culture informed by a combination of advanced technologies, theory, and philosophy. So my own history in exploring AI and machine learning started in Vienna, of course. Vienna is home to one of the world's oldest clusters of research on artificial intelligence, the OFI, the Austrian Institute of Artificial Intelligence, an offspring of the Österreichische Studiengesellschaft für Kybernetik, a registered scientific society founded in 1969. And about 30 years later, in summer 1998, Sandra Manninger and I were sitting around in a Schanigarten in the court of the Baroque ensemble that houses the OFI in the heart of Vienna. And we were discussing the possibilities of integrating artificial intelligence into architectural design with Professor Trappel, the director of the OFA, and Dr. Arthur Flexer, who you see here in a video that we recently put online, where we discussed certain ideas that came out of that research. Of course, this was a purely hypothetical conversation, since neural networks based on computational processes were in their infancy. With excitement, and of course, while sipping on a melange, they told us about a recent success back then, the simulation of one neuron to one neuron interaction. So you can imagine that that's a while ago. Some years later, in 2006, Sandra Manninger, myself, and Dr. Arthur Flexer conducted the first machine learning workshop at the Urban Strategies of the Angewandte. And then after moving to the University of Michigan, we started a collaboration with Michigan Robotics and Computer Science, which paved the way to a couple of new design techniques. And I would like to thank at this point, particularly to the director of Michigan Robotics, Jesse Grizzle, and the PhD student Alexa Carlson, who have been crucial in this collaboration. But first, let me give you a little bit of historical context. So the desire of us humans to attempt to the imitation of thought processes with the help of synthetic matter seems to be firmly wired in our mind. There are many examples of this, but I will point out two of them. The first example is the story of the Golem of Prague, beautifully brought to the screen in the German expressionist version by Paul Wegener in 1920. A golem is an animated anthropomorphic being in Jewish folklore that is created entirely from inanimate matter, usually clay or mud. The word was used to mean an amorphous, unformed material in psalms and medieval writing. The story goes that Rabbi Judah Leib ben Basazel used this method in 16th century Prague to create a golem to protect the population of the ghetto. What is astonishing to me is that a scroll with magic spells is placed in the golem's mouth to bring him to life, akin to programming or scripting. Language serves to bring inanimate matter to life, and of course he goes haywire. Let me give you an example that is not set in folklore or myth. And I apologize here for the poor quality of the movie, but it is too good as not to be shown. The story of the Turk is quite a fascinating one. Built in 1770 by Johann Wolfgang Ritter von Kempelen, it was designed to impress the Empress Maria Theresia. It was first displayed in summer 1770 in the Schönbrunn Palace as a chess-playing automaton and astonished the audience. On its tour through Europe, it defeated some of the time's most formidable minds, such as Benjamin Franklin, Frederick the Great, and Charles Babbage. Napoleon Bonaparte tried to cheat to win, but the Turk didn't have it and just wiped the board clean of all figures with his arm. As it toured Europe, it started to inspire more people to engage with aspects of automation and most likely triggered research on automated looms, such as in Edmund Cartwright's research, and even Babbage's difference engine. However, it was an elaborate hoax, as a person was sitting in the machine operating levers to make the Turks move. I like the idea that a Viennese hoax triggered the first modern wave in exploring artificial intelligence. And when we're talking about Babbage and the difference engine, Lady Lovelace is not far. The intimate relationship between computational processes and the human imagination emerged right there at the very beginning, when the first programmer and the first machine converged. In 1842, the ink on Lady Lovelace's seminal notes on the Turinese mathematician and scholar Luigi Menabrea and his sketch on the analytical engine was not even dry yet when she proposed that the machine could also be used to compose music. This marriage of computational tools and cultural exploration has not lost its edge to this very day. On the contrary, the emergence of artificial neural networks has infused fresh life into the conversation around the culture of machines, capable of synthetic reason. Before this potential area of cultural inquiry could be explored, the technological framework had to be created. As in so many cases, war is the mother of invention. Just in case that the Cold War turned hot, scientists were tasked to explore the potential of neural networks to perform feature recognition. Ultimately, the goal was to manage an entire array of cognitive tasks. Frank Rosenblatt was a main figure in pushing forward with inventions such as the perceptron and the concept of connectionism. And there is still this debate going on till today about the connectionism versus computationalism, which are two concepts that emerge from neuroscience. And you might already have heard that neuroscience plays a big role in the development of AI in general. The translation of basic neural patterns allowed to explore tasks such as solving mathematical problems, rudimentary translation, text creation, and feature recognition in images. These early experiments grew into what we see today. And we're talking here about like mid to late 1950s. Artificial intelligence is deeply embedded in our everyday life. Neural networks help diagnose medical cases, make decisions on bank loans, decide parole cases, read your bank checks, filter job applications, drive cars, fly drones, detect fraud, translate text, and recommend to you which book to read next. They are part of our households in the form of quasi-intelligent thermostats and security systems, help finding our way in our cars by using adaptive maps, and are close to the human body in the shape of our smartphone and watches, monitoring your moving patterns by day, your breathing patterns by night, and your heartbeat all day long in order to estimate your health status. They recognize your face and the way you type and help you photograph like a pro. Among many other things, the data generated by all these activities aid in perfecting the training of all these algorithms. In other words, AI is everywhere. However, what we currently perceive as humans of the AI ecology is just a visible part of the iceberg. The unglamorous, massive dark underbelly of artificial neural networks providing intelligent services, managing the gargantuan amounts of data on servers, organizing the routes data takes, controlling traffic lights, managing shipping, subway schedules, and many other mundane tasks elude our field of vision. They operate, as Lev Menovich put it in his book AI Aesthetics, and I quote, in the gray everyday of the digital society, end of quote. So how does this ecology influence the production of culture? And here a little excursion on aspects of aesthetics and AI. Considering the ecology laid out in the previous section, it seems evident that the tasks designed at the dawn of the machine learning in the 1950s, such as natural speech recognition, image recognition, automated translation, and others, can be considered a smashing success. Perceptrons, adaptive linear neurons, and probabilistic reasoning paved the way for the current state of our automated ecology. However, what might be maybe less apparent than the way how artificial neural networks have become part of our everyday life is the impact that they have had on cultural production. AI has increasingly become part of the arts. In doing so, it provokes, of course, a discussion on sensibilities and aesthetics in this new field of artistic production. Just to illustrate my point, let's have a look into Mario Klingemann's work. Just one example under many, but very useful because his process is clearly laid out in a series of interviews. Simply put, a large data set of portraits from Western art ranging from the Middle Ages to around 1900 are used to train a neural network. The result is a latent traversal through the latent space of a style gun, trained on portrait paintings. Behind this technical explanation lies a strange universe of unseen but familiar paintings, softly fused heads with 4 eyes, grotesquely distorted figures in pastel tones, merging expressionist contortions with the smooth features of classicist paintings. The conventional use of style gun is continuously demonstrated by websites such as This Person Does Not Exist, which wows its audience with the capacity to create convincing realistic images. People that do, well, not exist. Could there be anything more boring than that application for such an interesting algorithm? Perfect curve fitting can produce realistic images, and in most cases of conventional AI applications, this is a desired result. However, by shying away from the perfect curve fitting, something happens, the emergence of a different aesthetics.
Machine learning, or ML, is part of applied AI, and this is actually the field the tool sets or models we currently use in design and construction of the built environment are located. So how does this technology change the way we conceive, conceptualize, create, design, fabricate, construct, as well as maintain our built environment? How does it change the role of the architect? And how does it change the way how and what we teach? It is most certainly researched for its capacity as a tool for expedience. This is an example from research of the Technical University Munich, coming from the fields of computer vision and so-called digital twins. This machine learning model is being trained to recognize parts of the construction site, like columns or scaffolding, parts that then will be connected to a BIM model to collect projected and actual construction progress. But an ML model can also be used as a tool for surveillance, like this older example from a research project of the Hong Kong Polytechnic University from 2017, where the scientists observed individual workers' productivity. So I think this example clearly shows that we as architects have to engage in this conversation. Before we can start to look for possible scenarios, we need to get to know the individual constituent elements of this technology to be able to employ them in a way that, while using it for convenience, expedience, and service, also empower new forms of creativity and go beyond superficial forms of so-called ecological design. So what are these constituent elements? Machine learning relies on the acquisition of copious amounts of data, whereby the data can be of any form or shape. In supervised learning, this data is being labeled or tagged. So each of these sets or letters would be labeled as a 3, as an 8. For some, we would probably have problems to distinguish is this a 4 or a 7 that is actually being trained. And in unsupervised and reinforced learning, the model is trained to find hidden structures within the bulk of these data sets. So the second constituent is a mathematical model with its corresponding loss function, and in its simplest form, this model can be a line or curve. So in its simplest form, we see here a regression model with just a line, a linear regression model. But in most cases, it is a multidimensional surface or tensor that either needs to go as close as possible to all data points or separates them into classes. So machine learning is actually a geometrical problem. And although the mathematical models do have weights and they also have a so-called bias, the actual bias that is being discussed and criticized in the realm of ML is the bias that is generated through the acquisition of data sets. And that is exactly where we as designers and architects engage with ML. Rarely will we be choosing the specific mathematical model, at least not in the beginning, but we will be asked to collect, train, and if necessary, label the data sets the neural network will be tested on.
A couple of years ago, I had also this set of students, Hannah Dougherty, Mariana Moreira de Carvalho, and Iman Suleiman, who created a set of data sets, databases of specific architectural figures, doors, columns, stairs, variety of different things to train a neural network to create outputs. What I thought was really ingenious in this example here is what you see here, which was a class that consists of their own images, their own renderings. So the logic behind it was to test whether it's possible that a neural network can learn your own specific sensibility as a designer. This is a resulting example, for example, when you see here on the left side, one of the original renderings, and on the right side, it's a neural style transfer between their own renderings and the Baroque chapel. You might all know these examples of style transfer, where you have a Van Gogh painting, you have a conventional Grachtenhaus thing here, and then you get a result that is a combination between both. I would like to point out that certain things that we learned, and several other people also noticed already, is that if you use similar perspectives between your style image and your target image, you get better results. Just as a side note, if you want to try it yourselves. How did we apply these ideas then in specific projects. One of the main things we did first was playing around with city maps. Satellite images seem to be particularly well fitted for this sort of experiments. And we like the idea that we can actually take historical data and understand that because we have, I think I recently tried to figure it out, we have about 7,000 years of plants. And because we have those maps and plans and this long tradition of making plans and maps, we have enormous amounts of data that we can use. And that's what we're trying to do, like including historical data in order to explore this. And the way how we achieve the data or got to the data is also maybe interesting by using scraping. Scraping is a very popular method in machine learning exercises where you have a couple of lines of code that allow you to scrape the internet for images that have specific titles. But I can also tell you from own experience that you have to be a little bit careful with what you're doing there. I think 2 years ago, we created a data set that was supposed to be about Goth architecture, and we created a scraping code that was scraping the internet for images titled Goth. Now you can imagine what we got out of that search. Like about 20% were useful. I'm gonna jump over this here. But some of those were interesting results, like for example, this one where we started to have some fun basically speculating about cities on the moon. So this would be, for example, on a crater. And we particularly looked for 19th century science plates of the moon and Nolly maps of Barcelona, Rome, Manhattan, Washington, DC, and created these mashups between the moon and the Earth. These were entirely speculative projects at the very beginning of our research that were really helpful in grasping and understanding what these neural networks are doing, and also gave us a better understanding of how we can control it a little bit more. Although there is always the notion of, do we want to control it? The more I apply these techniques, the less I want to control them too much, because I think that the uncontrolled results are most often the more interesting ones. But that again talks more about us as humans and how we understand the world, in that they allow us to interpret things. We started with the idea of urban fictions, which instead of using vector graphics and Nolly maps, was really interested in generating something that looks a little bit more convincing as a possible city, with a variety of mashups between landscapes and urban textures. This is an example where we used an Indian landscape and Venice, or this is somewhere in China. This is Chandigarh and Vienna as a combination. And then, of course, also the idea to use your own sensibilities and specific textures, like in this case, where I used renderings of specific textures that I had designed with textures of Vienna.
Usually, before we introduce these new techniques to our students, we go through our own research and apply a variety of models to different data sets. Here, a neural style transfer with pre-trained weights seemed to be quite successful for the generation of landscape and urban conditions. Again, combining it with my own or our office's sensibilities. So here, this city does not exist. It is generated by an algorithm using pre-trained weights that have learned on the famous ImageNet dataset that contains over 14 million labeled images. We were using these images to train the neural net to recognize distances between infrastructural elements, population densities, scales of subdivision or block sizes, even building heights, to integrate them later into BIM software, for example, to calculate wind loads or potential flooding.
So another method is, of course, using style GANs. This has been very popular recently, an application a lot of people have been using, because they produce really compelling results, especially if you're not training them perfectly. What I mean by that is that, specifically speaking, neural networks in general are sort of a glorified curve fitting algorithm, meaning that you have a specific curve that you want to touch on with your results so that they get realistically looking results. So you remember that example of this person does not exist. This is perfect curve fitting. So it really achieves the point where it's so close to that necessary curve to make a realistic image that it looks completely realistic. But if you move away from that curve, when you do not perfectly fit the curve, that's when interesting things happen, like the ones that you see here. So we used actually a data set of thousands of Baroque plans that we also manually deformed and mirrored, and just to increase the possible variations. You need at least 1,500 examples to get to a feasible result in a style transfer, in a neural network exercise. Yeah. And then we applied that to modern plans. So we had a set with modern plans. These were some of the results we got out of that exercise. But more fascinating to me are the ones where you really move the weights of that neural network to become something different. These are the ones that are where we tweak the weights to not as close to the curve. And one of those results in further elaboration is this. And what I really like about this result is that it's a really weird result in that it has the voluptuous pochés and thicknesses of Baroque buildings, but at the same time, it inherited the asymmetry of a modern building. There is like the strange visual DNA still present in this image. And you have to think about it like this, that when we could make this to perfectly emulate a Baroque plan, but as I stated before already, I don't think this is the more interesting approach to do this. But the moment where elements like estrangement, defamiliarization, ruination come into place is where they become provocative in terms of their architectural meaning for the disciplinary work, where they start to operate slightly outside of what we know, in order to provoke our mind in seeing the familiarities in it, but the estrangement at the same time.
Working with computational tools and techniques, we always use three-dimensional and generative modeling. Our work was inspired by the amazing architecture of Ray Cappy, Frank Lloyd Wright, John Lautner, other flows, or in other words, the round plan or space plan rather than stacked floor plans. If we wanted to integrate the quality of these architects and the ability of space into a neural network flow, we had to find different machine learning models and even more laborious create our own 3D data set. This was the first attempt, a neural renderer model developed at the University of Tokyo. It is taking a 3D mesh geometry and a style image, adds texture so creates a new mesh. It was not yet what we were looking for, but a reasonable next step in this research. And we also had a special project with a very special client. These are two of them. We had been collaborating with Michigan Robotics for a year on studio projects and paper presentations. They asked us to design a robot test ground for the multi and bipedal robots. The robot garden needs to have a series of different geological features to test the robots: sandy terrain, rocks, grass, earth, etc. We created a database with several thousand satellite images of various terrains to train a neural network to hallucinate these features on a given mesh model. In addition, we created several data sets of architectural features, such as fountains, columns, etc., and styles such as Gothic or Baroque. playing with the weights, and we started to get a grip of how to use the technique until we got usable results. Making steps into the landscape was a requirement of the robotics lab, as well as the water feature, which will allow for flooding the robot garden to test the robots on slippery surfaces and in winter on ice. So here you can see the variety of models that we hallucinate to create features and some stills from the hallucination process. And an image from beautiful errors or glitches, that's the moment we are living for.
So deep dreaming is another technique you might have heard about. It's a very interesting technique in terms of what it does. It basically takes a target image and then applies particular features to them. And why is it doing that? Deep dreaming, you have to imagine it like this. I explained before how a neural network can learn specific features, right? So you go through a variety of layers, they learn edge recognition, feature recognition, etc. Now, what's happening here is that the flow of information is inversed. So instead of recognizing or detecting features, it tries to understand features. There's a difference in that, meaning that if it has, for example, in this case, it has a data set of lizards, birds, and feathers. And so this neural network could recognize in any photo whether there is a lizard, a bird, or a feather. And if there's nothing there, then there's nothing there. On the other hand, if you reverse the flow of information and you give this neural network an image and tell him, recognize this, what is this? Then it's going to try to make sense of the world by the knowledge that it has, which is lizards, birds, and feathers. So it's going to read those features into the given image. That's why it transforms it into this nightmarish image of Van Gogh turning into lizards, birds, and feathers. Post-human perception of the world. You might have heard about machine learning. It's getting widely, machine vision. This is getting widely applied in automated cars, robot vision. And what you see here is such an image or an example of robot vision or machine vision based on LiDAR, light detection and ranging, which is a method that estimates the distance to objects. But that is not all. It needs to understand what is what. And for that, it uses a variety of different neural networks. One thing I'm obsessed about here is not so much the nature of the neural network, but rather the strange perception of the world that comes with it. So it seems that we're suddenly starting to share a vision of the world that is different to ourselves. And I'm really surprised how it sees palms and distance. And a thing on the left side of this image is a human figure that obviously was captured really badly. And this is actually allowing for a new way of understanding or seeing the world that is different to what we as humans are used to.
The first project we applied a neural render model was actually designed for the competition for the Austrian Pavilion for the Dubai Expo in 2020. It was our first successful AI-driven project. The ceiling of this project is a 2D to 3D style transfer acting between Baroque sensibilities as a style and a series of modern ceilings as the target. The result is a strangely articulated ceiling that oozes Baroque presence. The floor is intentionally kept modern to create a space for the tension between modern and Baroque sensibilities. The next work is based on a collaboration with Computer Science Michigan, who are using a powerful neural network architecture for machine learning on graphs. This was our first exploration to work directly on 3D meshes. The question was, can we collect 3D models from the hand of a designer, creating a large database of models in two distinct categories, houses and columns? in order to train a neural network to come up with additional model solutions that are generated using the learned features of the trained network. As said before, to create a design strategy that employs actual 3D geometry, we had to find the right model architecture, and we even more so generate a data set of 3D models. This is a screenshot of a geometry created for this dataset containing around 1,500 labeled OBG mesh models of specific architectural classes, houses, and columns. It was the labor work of summer 2020. We refer to this dataset as the sensibility dataset. The next step is to train a graphic convolutional neural network on this dataset to learn a mapping function between the Cartesian coordinate space of 3D models to our defined label space of sensibility features. And the next step is, and the final step is to placing the trained graph convolutional neural network in an optimization framework that takes in a user-specified 3D model as input and then deforms the vertices of this model to optimize the shape of a user-specified style, aesthetics, or functionality label. So how can a neural network interrogate the inherent sensibility of a specific designer? So after our research, we can assume that we can model a designer's sensibility as a high dimensional function that can be learned from 3D models and applied to generate novel design solutions. The design technique, whose backbone is graph CNNs, is capable of modeling both the perception and creation of architectural objects. And you can read more about this project in the paper 3D Graph Convolutional Neural Networks, which we presented at Acadia in 2020.
Another project where we applied a completely different approach. Again, there's so many neural networks out there. I can tell you, like, there's for every problem, there's a neural network. So you can really, by just looking around, find incredible inspiration. And what we did here, for example, is that we used a neural network that is designed to create images out of language. I know that they have become quite popular in recent time with DALL-E and similar methods, but this was a little before those networks came out. In this case, we used an attentional neural network that we trained basically by describing parts of the architecture with language and seeing with what images it comes up with. And out of those images emerged then the entire project by using a rather simple technique of extruding volumes in order to create the entirety of this school. It was a competition in Shenzhen. We didn't win the competition, but the funny thing is that somebody saw this project and has commissioned us now to, using the same technique, do another school somewhere else in China. And he was particularly attracted by the incredible coloration. This is also very telling here in that we have a specific problem with using neural networks in architecture, in that they can either generate an interior or an exterior, but not both at the same time. And we've been trying to deal with the problem and see how we can either weaponize the problem by very specifically separating again interior from exterior, or by simplifying the interior, which we made in this case. We really created a primitively simple interior with these highly articulated exteriors, which also was, of course, was really helpful in terms of the budget for this really big school. It's a school for around 3,000 students. It has about 200,000 square meters, sorry. It would have been a nice project to build, but I'm looking forward for the school that comes next now.
So what does it mean if we are being assisted by tools that learn, when we move from using expert systems to learning systems, when we live with robots and machines, when we extend our senses through an added perception of the world? Can these tools extend our creative potentials, and will they aid us in representing scientific and mathematical concepts of space? Who will be the curator or advocate of data, the data we acquire and the data we produce? And who will be the participants in the design protocols that we are about to generate? These are the questions we discussed recently within the neural architecture group. Matthias Del Campo and I started together with Daniel Bolochan and Emmanuel Ko. And we discussed these topics also at the Areti Lab, the Laboratory for Architecture and Artificial Intelligence, a collaboration with Taubman College, Michigan Robotics, and Computer Science Michigan. And I also take the opportunity to shamelessly refer to Matthias Del Campo's upcoming publication, Neural Architecture with Oro, that should be available end of this year. And also I have to apologize due to the brevity of this talk, I had to leave out a lot of technical details. If you want to know more about them, there's a series of lectures and tutorial videos on our YouTube channel. And that was it. Thank you very much.
Thank you very much again, Philip and DigitalFUTURES for the possibility.
Thank you. Thanks a lot to Matthias and Sandra. And is there any question from the floor, from the audience here? Welcome to put forward. Hi, Matthias. Hi, Sandra.
Hi.
How are you?
I'm good. Thank you so much, Philip. How are you? You must be
very busy for the yearly event, right? We're looking forward to have you in the future. Pandemic make it's impossible traveling, but looking forward.
Yeah, I'm hopeful. Yeah, it's a fantastic event. So congratulations, Philip.
I want to ask a question. This morning we talked to Daniel. He also made another lecture, but a little bit different to yours. I think a different perspective to understand the artificial intelligence in architecture. I think Daniel's perspective a little bit quoting from Costas and the knowledge, which is about searching for the possibility by AI, because all the potential possibility is there. So Daniel is present the data set in the Himmelbau office, including the plan sections and all the image photos they have shot before, and make a new creative process to doing some to find some new non-existent building, but the style is Himmelbau style. So there's like a searching process in expert system. So I give him a question, but at the same time I think I want to give to you, because in both of your research and project I find some different, because what you are doing actually is searching for something not existed. And that means, for example, in the high school project, it's totally a new design, but actually you implement the machine learning as a special tools to generate the form. So I think it's a big difference between Daniel and you. So would you like to make some statement on that, about the creativity and about the imagination and about the scenarios, how we can make a full use of artificial intelligence in architecture?
Just as a starter to clarify, I think we have applied many different machine learning models. So one of which was also the same that Daniel was using for his research. But we, as I told you, I think we were really interested in how we can work as designers with and how we can add it to our creative processes. I think both Matthias and I agree that at this point, the AI is not capable of really to be truly creative, at least with the models that we have been working. But they are but for us, they are inspiration to add to our and extend our own creativity. Probably Matthias wants to add more to this.
Yes, I agree with Sandra that it depends really on the the variation and the goal that you're setting yourself with this approach. Like, for example, when we can take two things, like we've done also work where we use data sets of our own renderings, for example, and images. All the images we've done in the last 10 years span, we used recently in one data set. And this was interesting because it was about exploring what are the points that connect all our work together. Are the main features that come out of this process that tell something about the style of span? Is there something like a style of span? I'm not sure. Yeah, but it's on the one side, the whole AI thing is a research tool. On the other side, it can be, as Sandra mentioned, a tool that inspires you to be creative and solve things creatively. Yeah. And we only showed like a very small range of what is possible with it, because I mean, we obviously are interested in using it as a generative tool that allows us to explore possible design spaces, meaning what's the range of designs I can do for a specific project. But on the other hand, you can go also completely conventional with it and do things about, analysis and optimization and all these sort of things. So there's like a wide range of things you can do. The main connection between maybe people like Daniel, ourselves, several others, Deep Himmelblau and so on, is the obsession with understanding that we can now finally use machines that are probably able to provide us with possibilities that we did not see before because we couldn't explore them, just because of the calculation power necessary to do it, because of the algorithms that were not there yet, but now they're there. I mean, you saw in our lecture that we started using or talking about AI with people in the late 90s. And now it's finally possible to do this because the technology catched up so much that we can actually use it. Does that answer your question?
Yes,
I'm not sure.
It's interesting because because I also implement artificial intelligence in my studio this year, but I find it's a lot limitation actually, although it can produce a lot of potential possibility to generate form, but at the same time, the logic is leading to another stylistic because it should be in control by different kind of ways of thinking. So that's maybe the first question I want to ask. The second question, I think it's a very important or impressive trend right now in artificial intelligence because so many expertise and researchers are doing this. But I find it's quite different in different schools. For example, in Europe, in the last few days, I invite Achim Menges and also Philip Rock. They implement artificial intelligence not totally in the formalism level. Probably they just deploy this kind of machine learning tools in certain process to update the certain process of their design. For example, Philip Rock, they implement in the structure, performance, statics, formation, and not the whole process. But that is maybe a problem-solving process to make use of AI. But you guys, I think, is totally jump into this kind of new trend and try to leading and setting up a new linguistic ways or the stylistic ways in architecture. So I mean, both of this kind of research are important. And how would you like to address a manifesto from your office and from both of you by make use of the new architecture? How would you like to manifesto new neural architecture and make a conclusion on that, please?
Yeah, I mean, first and foremost, Sandra and I think agree on that it's not a style, because it's so widespread. It's so much embedded in our whole life. AI at the moment, neural networks are all around us. They're already there. So it's nothing that is futuristic. It's not the future, it's the now. Yeah. And what I think is very important for architects is to engage with these tools as soon as possible, because if we don't engage with them, somebody else will do it for us. And then we will not be relevant in that conversation, neither culturally nor technically. And I think we have to engage this from both sides, the technical side and the cultural side. What does it mean for the architecture discipline to be part of this novel ecology of design, which is probably the first 21st century design method, by the way, because everything else that we have been using in computational design was already developed in the 20th century, was just refined in the 21st century, but not the AI research. That's something different. Now, given that opportunity, it means that we can engage with architecture on a level that is multifaceted. It is, at the same time, it can be about optimization, as the examples that you were speaking about with Philippe Bloch and Achim, but it can be also profoundly a cultural conversation, understanding what does it mean to be human in a time where we share agency, authorship, maybe even creativity, we don't know that yet, yeah? But when we are part of a post-human design universe where we are not the top-down designers of things, but are actually meeting halfway in a bottom-up, top-down design method, how does this express in our culture and what does it mean, even philosophically, theoretically, aesthetically, and so on. So there's like a whole field of things that are in question right now, which are part of architectural discussions that are on the table. And I think it's very exciting that we have the opportunity to live through this time, to be part of that, and to contribute to this idea.
Great. Thanks a lot. I think it's time for us to end your keynote speech because our workshop opening will come in very soon in 5 minutes. So we need to quit this Zoom and participate to another room, change to another room. So great thanks to Matthias and Sandra and contributes to the Digital Future community. And thanks a lot for your lecture. Bye-bye.
Thank you for the invitation.
Thank you so much for having us. Thank you.
Yes.
Bye-bye.
Bye.